cannot talk of any kind of microscope or thing. So it is that indirect way of elucidating the structure, how atoms, ions are sitting in a particular molecule. That's why a lot of mathematics is involved in it. So for doing, if a student has to do complete work of a structure, it will take months. If he does not take use of the machine these days, earlier when we were doing one structure, it takes 1 year to solve it. So this is the only difference of earlier technology and the modern technology. So the effect of this is happening because although we can now more these days with the machine, but we lack in understanding the concept. So what happens when incoming X-rays fall on a crystalline material? So electrons, they vibrate with the same frequency. The electron cloud sets electron cloud into oscillation. So this also sets nucleus into oscillation, small effect which we can neglect. Here we cannot neglect the effect. So oscillating charges re-radiate in phase with incoming X-rays. So these radiations which are generated due to oscillation of the charged particles, they are what we are getting as scatter radiation from every electron. So diffraction is wherever these radiations reinforce each other, they combine, they destructively interfere or destructively interfere, so we get a very huge part. We get a better physical picture of diffraction by using Lave's formula leading to the Lave's equation. So when we do Lave's experiment, we keep our crystal stationary, so in that case your theta is fixed. However, a parallel approach to diffraction via the method of Bragg, where diffraction can be visualized as a reflection from set of. So this is the difference between what Lave said and what Bragg did. In 1912, Lave gave the phenomena of X-ray diffraction. So he has taken the picture. Lave's theory is much more valid. In fact, it is only valid when we talk of diffraction. But for understanding the concept, Bragg's idea is okay for making students to understand. Approach of Bragg is easier to grasp. Let us consider a coherent beam of X-ray impinging on a crystal with the dummy plate at an angle theta to the X-ray. Now what happens? Incident and scattered waves are in phase if in-plane scattering is in phase and scattering from across the planes is in phase. We will in the next slide see what is the difference between in-plane scattering and what is the difference between across the plane in phase. Incident and scattered waves are in phase if in-plane scattering is in phase and scattering from across the planes in phase. Lave postulated, two postulates, very important postulates of Lave. What are these? Crystals have a periodic arrangement of atoms. अगर क्रिस्टल में periodic arrangement atoms का होगा, लावे ने यही दो postulate दिए थे. दूसरा क्या दिया? X-rays of wave. उस वक्त तक ये नहीं था कि X-ray का wave character भी है कि नहीं. उसने दिया था concept which were not confirmed till then. 1912 में ये concept तब तक confirm नहीं हो पाया था कि X-ray they will act as waves or they will act as particles. So then crystal should act like a diffraction grating for X-ray. Because he said wavelength of X-rays is of the same order as the planar distance. So जैसे एक grating काम करती है visible light के सामने, इसी तरह crystal एक grating की तरह act करेगा X-ray के सामने. These were the two postulates, very important postulates of Lave. Both these postulates were proved by a single experiment of Lave. Lave ने जो experiment perform किया 1912 में, इसमें दोनों में इसने ये verify किया अपने postulate. So you can see this is in-plane scattering. Let us consider in-plane scattering. So X-rays are falling, they are falling on this atom of the lattice, get scattered. Similarly on Y they get scattered. Now what happens? This ray, it has traveled this distance xv much more and a by this green ray. So if xa is equal to by, then
ते पॉवर बैंक
they are in
चार्जिंग
phase.
लावून आले.
Extra power traveled by incoming waves AY. This wave, this is the extra distance traveled, and for this wave XV is the extra distance traveled. So this is the incident angle, this is the scattered angle, but this is still reinforced scattering and not reflection. So इसको भी हम reflection नहीं कह सकते. Here we are getting, अगर हमारे पास strong peak आ रही है, strong part आ रहा है, this is due to scattering, in phase scattering. So this is what Love's picture. Now we will come to the Bragg's picture. Bragg's equation क्या कहती है? Let us considering
मॅडमचा फोन बोलायले आमच्या
Love
इथल्या
ने across the plane की बात
कॉलेजमधून रेणुका बोलते.
की बात की. X-rays they fall on the constituent particles
आवाज
of the
ओळखायला
material.
ना का?
They become source of electromagnetic radiation.
ते पॉवर बँक मी चार्जिंगलाच लावून आले. घरी जाणं झालं तर तेवढं काढून ठेवा की ते ह्याला लावले सोलरच्या चार्जिंगला. चार्जिंग पॉवर बँक सोलरचे ते चार्जिंग लावले होते. गरम होऊन फुटायचं काय तर व्हायचं. लक्षातच नाही माझ्या.
इंटेंसिटी हमने ली इधर भी 100 है, लेकिन इस केस में ऐसा नहीं है. इधर हमने 100 ली,
माझं ते सुरू आहे ना रिफ्रेशर आजपासून.
दिस इज व्हाट डिफ्रैक्शन. दिस इज व्हाट ब्रैग से ये एक्सरे जो आ रही है रिफ्लेक्शन के बाद 100%
तुम्हाला पोस्टर भी जायचं की.
सिमिलरली रे 2 इट इज ट्रैकिंग एट बी फ्रॉम ऑन दिस प्लेन इट इज गेटिंग रिफ्लेक्टेड लाइक दिस. Similarly, ray 3 coming like this. Now, what is the path difference between A, B, C? आधी wave इधर आ गई, आधी wave इधर आ गई. So एक wavelength हो गई. So path difference between ray 1 and ray 2 is one wavelength. So this means here wave width is like this. So crest of this wave is falling on the crest of ray 2 and trough of ray 1 is falling on the trough of ray 2. So here amplitudes they will get added, so we are getting here respectively. Now, what happens for difference in ray 1 and ray 2? 3 कितना होगा? एक wave इधर complete हो गई, इधर एक wave complete हो गई. So 2 lambda. So between 1 and 3, then 3 lambda and so on. If it is like that, we are starting with ray this like this. Here also we are getting like this. So at C we are getting like this. So this means it contains one wavelength, two wavelengths, three wavelengths. But this thing we cannot calculate or we cannot make out whenever we collect data. What we are getting is we are allowing X-rays to fall on the sample, and this we are getting a whole information regarding how atoms, ions, molecules they are sitting in the crystal is contained in this scattered part. So it is up to us to extract information of the unit cell, length of the unit cell, symmetry, point group, space group, how they are sitting, what are the intermolecular interactions, hydrogen interactions, CHO, CH5, pi-pi interaction. So all information is contained in this scatter radiation. Now, how we can calculate it is up to us, our expertise, कि हमने इस डेटा से निकालना है जो कुछ भी निकालना. हमारा इनपुट सिर्फ यही है जो स्कैटर्ड हो गया है, इसमें ही सारी इंफॉर्मेशन कैद है. आप कैसे निकालते हो जी आपकी एक्सपर्टीज है. हमें इतने साल हो गए, अभी भी हम केस स्ट्रक्चर जो डिफिकल्ट होते हैं नहीं निकाल पाते. इट टेक्स अस मंथ, इवन अ ईयर टू सॉल्व सम स्ट्रक्चर. देन वी आल्सो टेक हेल्प ऑफ सम सीनियर पीपल हु आर वर्किंग इन दिस फील्ड. सर ऐसे नहीं ऐसे हो रहा है, गाइड अस. सो जो सीधा निकल गया स्ट्रक्चर निकल गया, जहां एक बार कहीं अड़ गया तो अड़ गया. देन यू नीड सम crystallography background, otherwise you are unable to solve it. So कहने का मतलब है कि हमारा सिंपल एक्सपेरिमेंट है एक्सरे डिफ्रैक्शन स्टडीज का. आप एक क्रिस्टल लेते हो, उसको माउंट कर देते हो, इंसिडेंट एक्सरेज उसके ऊपर डालते हो, एंड व्हाटएवर इंफॉर्मेशन यू आर allowing to fall on it, this information you collect on a photography film nowadays, on a CCD camera, or whatever be the method, counter method. So all your information is now there. So you have to calculate your structure, you have to make a picture of your structure. So from this scattered radiation. So So you should have a clear idea what is happening here when X-rays are falling on a crystal, how your lattice is behaving. Now, a portion of this is shown for clarity. Only we have shown a small portion because here it is thousands and thousands of atoms actually in the crystal. For destructive interference to occur, many planes are required. Then we take planes, only these 4 planes. There is nothing like destructive interference. Here it is only constructive and constructive. But this is not the picture. Some planes are like this. Some planes are like this. One plane, if I take it, will come like this. It is not that 1, 0, 0, 2, 0, 0, 3, 0, 0, 4, 0. Plane can be 1, 2, 3, 1, 3, 8. It can be in every direction. The interacting volume of X-ray is large as compared to that shown in the schematic. It is just a picture. Scattering planes have a spacing d. We have shown that interplanar spacing is d between plane 1 and plane 2. Now ray 2 travels an extra path as compared to ray 1. You can see here AB plus BC is the extra path traveled by ray 2. The path difference between ray 1 and ray 2 ABC. ABC is the path difference which ray 2 has traveled more than ray 1. So this path difference between ray 1 and ray 2, when we calculate, we take this as the right angle triangle. If this distance is d, then from right angle triangle, if this angle theta, it will come as d sin theta actually. Similarly, BC will come d sin theta. So it will become 2d sin theta. So what is the condition? It's not that we are saying that it contains one wavelength. Maybe it contains a half wavelength also. For constructive interference, this part difference should be integral multiple of wavelength. N lambda is equal to 2d sin. Our part difference is 2d sin theta. Constructive interference will happen when this 2d sin theta is equal to n lambda. What we call it as Gray's equation. So now this n is the main point that I have chosen this topic. So how to calculate this n? Or if I will modify my Gray's equation, I will remove this n because I don't have any way to find it out. The part difference between ray 1 and ray 3 is, now ray 1 and ray 3 is 2 times 2d sin theta, so it will become twice the n lambda. Similarly, this implies that if ray 1 and ray 2 constructively interfere, and ray 3 will also constructively interfere, and so on. If it contains one wavelength, then it has to contain 2 wavelengths, it has to contain 3 wavelengths, and so on. So because it is a constant interplanar spacing, so they will constructively interfere. Now we will come to this. This is the plane 1, this is the plane 2. Sometimes ray may be slightly bent or so. More or less, they will interfere constructively. That is the ideal situation we have taken. But sometimes this ray may be like this, slightly different from the constructive interference. You can see they are not overlapping on each other. So this case can also be happen. So in this case, amplitude will be added, so resultant wave will be this one, which remains same thereafter like in the BP plane. Okay. This is almost, first in our case, this is 100% constructive interference. This is almost constructive interference. Now you see, when we talk of this one wavelength, if I have to increase the angle, your incident angle is like this, maybe at 15 degree. If I increase it to 30 degree, then your power difference will increase. AB plus BC, although planes are same. We have taken D as the same. Here AB plus BC is less than AB plus BC. What this says? Path difference increases with angle. Sometimes you ask the student or in net में question होता, if there is incident angle is, if you increase the incident angle, what will happen? 4 options होती हैं उसमें. Your path difference will decrease, it will remain same, it will increase. You may student understand with the figure. If your theta is increasing, then your path difference will increase. So इसी तरह क्वेश्चन निकलते हैं, नेट के हो गए, इंटरव्यू में हो गए, whatever will be. और स्टूडेंट ने अच्छी तरह से किया हुआ, इसी में से 4-5 क्वेश्चन निकल आएंगे जो नेट लेवल के होंगे, इंटरव्यू लेवल के होंगे. So you can see here from the diagrammatically you make the student understand. You have increased the incident angle, similarly reflected angle will also increase. What will happen here? Your part difference will increase. How to see that part difference increases with angle? Clearly you can see angle A prime, B prime, C prime is greater than angle A, B. Now Lave versus Bragg. In Lave's picture, constructive and destructive interference at various points in space is computed using part difference or phase difference, given a crystalline array of scatters. So what happens? So constructive and destructive interference will happen depending on
अजून एक
your
पुस्तक
part
आहे
difference or
तिथे
phase
रेझोल्युशनच्या
difference.
लायब्ररीमध्ये.
Bragg
नाही इथून
simplified
आलं
this
एकच
picture
भेटलं ना.
by
नाही
considering
अजून
phase
एक ब्लू कलरचं
process
माझ्याकडे
as
हायमन घेतलं नाही.
reflections from atomic phase.
तसलंच पुस्तक सेम
आज
Whatever
घ्यायलाच
law
पाहिजे.
is
नाही
that,
तसलंच
Bragg
पुस्तक
also
सेम
did
लायब्ररीमध्ये
the
आहे.
same thing.
नाही
What
उद्या
instead
घेते
of
ना प्लीज.
नाही नाही आज घ्यावं लागलं आज
नाही तयारीच नाही मला
in
एकदम.
एक म्हणजे थोडं
Sometimes
सिलेबस
matter may
लिहून
be
द्या.
present,
हा,
sometimes
syllabus
matter
वगैरे
may
लिहून देईल.
may not be present
आपण इंट्रोडक्शन देते.
in a
हा
plane. If atom is not present, we will not get any reflection. This is called extinction. Some reflections are missing. So that is the main point. How you calculate whenever you have to solve a crystal structure, what you have to do? The first point is you have to find out the unit cell. What is your unit cell? A, B, C, alpha, beta, gamma. Once you have in your hand the 6 lattice parameter, then you see what is your crystal system out of the 7. If all the 6 lattice parameters are different, A, B, C are different, alpha, beta, gamma, they are not equal to 90, then you restrict your study only to triclinic system. This all you know. We have 7 crystal system: triclinic, monoclinic, orthorhombic, cubic, rhombohedral, trigonal, hexagonal. So your aim is to find out the crystal structure. So our first aim is to find out the unit cells. Once you have the unit cell parameters in your hand, so then you can decide what is your crystal system. Your crystal system depends upon A, B, C, alpha, beta, gamma value. Once you have all these 6 values, then your work is only one time out of the 7. Now you restrict yourself only to triclinic system, because once you calculated A, B, C, alpha, beta, gamma, you have seen, you have made it out that my crystal system is triclinic. So now I will leave the 6 crystal system. My work is drastically reduced. Now in crystal system triclinic, I have only 2 space groups, P1 and P1 var. P1 var is inversion center. So again, P1 and P1 var depends upon, once you collect the data, you what you get whenever you perform any X-ray diffraction experiment. You get from which plane how much intensity is coming. I say 100 plane is giving me 1000 intensity. 123 plane is giving me 100 intensity. 300 reflection it is giving 0. 400 is giving me 5000 intensity. 600 is giving 5000. 500 is giving almost 10 or 20.
Chemistry.
So what I have noted, 100, 300, 500 intensity is 10, 20, 30. Wherever 200, 400, 600 intensity is in 1000. So I have made even reflections are present. 200, 400, 600. So odd reflections are missing. So this is the from data which I have collected. My output is from which plane I am getting what intensity. Nothing else I will get whenever I will perform any crystallography experiment using X-rays on a single crystal. So my output is from which plane how much intensity I am getting. From analysis of data I can make out whether all reflections are present, whether even reflections are present, whether 120 reflections is present, 130 not present, like that. From then I will make some point that HKL, H even present, K even present, L even present, HKL all are absent, H plus K is 110, present 120 absent. This means H plus K even present, H plus K are absent. So from there I have made out, so which which reflections are present, which reflections are absent. So this has given me an idea of extinctions. So from extinctions, which reflections are absent, I can make out what is my space group. Once I make out, because in triclinic you have only two space groups, then in monoclinic we have number of space groups, P2, P21N, P21YA, P21YN. So depending upon your HKL data only, once you take international tables, so there is a book we call International Tables of Crystallography. In that all the 230 space groups they have given for this space group what are the reflections should be present, what are the reflections should be absent. Once I have data in my hand, then I make out what HKL is present, what HKL are absent. Then I open my international table for X-ray crystallography and see my reflections are matching to what space group. So out of the 230 I have to select one. Sometimes it may take some error. Instead of P21YA I decide P21YC. So that is your expertise, how you select it. So once you have made it that your space group is like this, say P21, then your work is reduced from 230 to 1. Otherwise I have to try 230 space group. Now you have restricted yourself to only one space group. Now you start your crystal structure determination. You have selected out of the 14 brevis lattices one that is permittive or non-permittive. That you can make it out by finding out Z. If my Z is coming 1, I will say permittive. If my Z is coming 2, I will say in triclinic it is P1 var. Because in P1 var, one atom is generated by applying the inversion symmetry. So then I calculate how many Z are present. For this I will do simple density experiment. I can do it in I take two solutions, then I can find out what is its density. From the density formula I can find out Z. That means number of molecules per unit cell. If it is coming 4, then I will say it cannot be triclinic, because in triclinic it can be either 1 for P1 space group and 2 for P21 1. So if it is coming 2, then I will see some other system, monoclinic or orthorhombic, depending upon what is the ABC values they are. So this is how we decide. What is the benefit of discussing all this is, so for any crystallographer, knowledge of extinction should be very, very important. Only on the basis of extinction, what reflections are absent, it is decided what is the space group out of the 230. Because you have your space group of crystal is 1 out of the 230. It is a very large work. So for this you should have full knowledge of this extinction, how to see what is the space group of your sample which you are studying. So we will come to the extinction. What extinction means, some reflections are missing. How they are missing, this we will study now. Bragg simplified this picture by considering this process as reflection from atomic plane. Since there are two Braggs involved, wherever we refer to the law of equation, it has Bragg. आप देखोगे बहुत सारी जो स्टैंडर्ड की किताब होगी वो ब्रैग को इस तरह से लिखेगा. This signifies both the brothers. आप जब हम ब्रैग पास्ता फैस लिख देते हैं, इसका मतलब एक है फादर एंड सन नहीं हुए. तो कई बार हम कहते हैं कि लिखने में जो गलती है यहाँ कैसे है. So this brag signifies both father and son. I don't know whether it is father or son. I don't know. So diffraction according to Bragg's picture has been visualized as a reflection from set of planes with interplanar spacing d. Diffraction should not be confused with the reflection. कोई भी पूछे स्टूडेंटों को, आप समझाओ कि कोई भी पूछे रिफ्लेक्शन में क्या आपको 100% इंटेंसिटी मिलेगी, रिफ्लेक्टेड रहेगी. डिफ्रैक्शन में हार्डली 1 or 2%. So what we are studying is diffraction, not reflection. It is only for our understanding कि हमने कहा कि X-rays are falling on a set of planes, they get reflected, and then we have brought the concept of reflection. So reflection occurs from surfaces. Because X-rays cannot be reflected from surfaces, it will penetrate. occurs throughout the bulk means throughout the sample. X-rays will penetrate and it will give energy to its constituent particles, which will vibrate and generate, themselves will become a source of electromagnetic radiation. So this reflection takes place at any angle, take place only at Bragg angle. Diffraction, because whenever Bragg's equation is satisfied, we will get constructive interference, otherwise no. 100% of intensity, this is the main point. 100% of the intensity may be reflected. So only very small fraction of the intensity is reflected, because mostly it is the destructive interference. In very few areas, it will be constructive interference. That's why there is a drastic decrease in the intensity. If n lambda is equal to 2t sin theta is the Bragg equation, then what is the famous Bragg's law? So, how we can define Bragg's law? Simple is, constructive interference will take place when part difference is integral multiple of wavelength. Or we can say, diffracted beam appears to be specularly reflected from a, specularly means like mirrors, reflected from a set of crystal lattice planes. So planes, they are acting as a mirror. So angle of incidence should be equal to the angle of reflection. Now we'll come to understanding the Bragg equation. Bragg equation is 2d sin theta equal to n lambda. This equation is written better with some descriptive subscript. So now you can see, if we are using copper radiation, 2d HKL sin theta HKL. From a plane d HKL, if it is 1, 1, 1 plane, so then theta will be also written as theta 1, 1. This angle is for plane 1, 1, 1. If this equation is satisfied, then theta is your Bragg's angle. So n is an integer and is the order of reflection. Means how many wavelengths are present. N signifies this. That is how many wavelengths of X-rays go on to make the part difference between planes. Note, if HKL reflection corresponding to n equal to 1 occurs at theta HKL, then 2 HKL reflection will occur at higher angle. So this is very, very important to filter out n from your formula. Agar HKL, if HKL refraction occurs at theta HKL, then for this what is the value of n? 2. Will occur at higher angle 2 theta 2h 2k 2f. If Bragg's equation is not satisfied, what will happen? No reflection can occur. If Bragg's equation is satisfied, what it indicates? Reflection may occur. So for large interplanar spacing, the angle of reflection tends towards 0. So when we go on increasing the interplanar spacing, because if I will increase d, sin theta has to be decreased, because this is constant. Wavelength we are taking constant, we are not varying it. If your d value is increasing, your theta has to come down. So sin theta decreases and so does theta. The smallest interplanar spacing from which Bragg's diffraction can be obtained is lambda by 2. Because maximum value of theta is your 90. So sin 91, so DHKL for n equal to 1 is lambda by 2. Maximum value of theta 90, we cannot go above 90. Since sin theta is 1 from Bragg's equation, your interplanar spacing should be half of the wavelength. Now you come to order of reflection. N equal to 1 signifies sin theta equal to where beta will be, we will take inverse, it will come 20 degrees or so. One first order reflection. One second order reflection, 220 from 220 plane, it is 49.3. Put the value, it will come 43.3. In XRD, nth order reflection from HKL is considered as first order reflection from HKL. We have to convert the formula. If it is coming from 222 plane, we have to convert it into 111 plane. 222 plane means if they say your interplanar spacing, if it is your 100 plane, or this is your 001 plane, then your 002 plane will come in between. If it is coming as two wavelengths, then I will say it is coming as one wavelength. I will convert it into phase. So we'll continue with this tomorrow. So now we will have a discussion whatever we have studied. Questions from your side. We'll continue with this. Hello.
Hello.
Yeah. Questions from all the participants. We'll have discussion. Whatever we have studied.
Sir, myself Anarsi. I have one question. You have said that we are getting the response we are getting the intensity in the diffraction pattern because of the electron density.
Because what we are getting electron density cloud.
Yeah. So if we have two atoms in ions form and having the same number of electrons, can we distinguish them that these two ions?
No. Whenever we talk of in ionic form, you are talking if I crystallize some sample in the ionic form.
No, I am saying that, for example, we have iron and titanium.
Okay.
And suppose iron is in +3 state or titanium in +2 state or something like that,
Okay.
in such a way that they have same number of electrons.
Okay.
So can we distinguish them? This is my question.
My answer is because whatever study I have to do in the crystalline form. Okay.
Yeah.
When I will make crystal, if your sample is in the ionic form, it will not get crystallized. It will take environment from the moisture or whatever will be the solvent. It will take one electron from there. So molecule has to be neutral. It cannot be. I cannot crystallize a sample say Na plus or Cl minus. It can never happen. You got my point. Whenever I solve such samples, so some water, hydrogen or oxygen, they will take electron, means they have to complete their valency. Molecule as such has to be neutral. It cannot be in ionic form. This you also know if you have studied chemistry. We cannot crystallize it in ionic form any sample.
No,
Molecule always is neutral.
Sir, my question is not that. My question is what I am saying that overall compound is neutral.
Okay.
And
whatever density I will get, so then atomic scattering factor of titanium or iron, whatever you are talking, they have different atomic scattering factors.
yes.
I have to feed the formula whenever I have to solve. If I will write titanium, it will pick the atomic scattering formula. If my results will not convert, then I will replace, because whatever structure I will solve, I have in my hand what chemical reaction I have done, and with whom, what are the constituent solvents or compounds I have taken to synthesize a particular compound. So I have to feed the formula. So what atomic scattering factor I have to give that my sample is, say I will write C20H20O4 S1. So when I will solve the structure, so the computer program, it will take atomic scattering factors of carbon, hydrogen, oxygen and sulfur only, not any other. Sulfur and chlorine, if you can say. Even if I wrongly plot it, say titanium, then I have a distance table in my hand. I say carbon sulfur distance is 1.66, carbon chlorine distance is 1.75. If I have wrongly put chlorine as sulfur, when I will solve the structure, I will see the distance of carbon and sulfur. If it is coming 1.75, I will immediately say no, it is chlorine, it is not sulfur. So maximum time chlorine. Sometimes we put some solvent to crystallize having chlorine. So it makes a reaction, it replaces oxygen and chlorine comes. So OH distance is also 1.34 or 1.33 approximately, and CF distance is also of the same kind. So then your results will not convert. Then I put the chlorine in the formula, then it takes atomic scattering factor of chlorine, and then it does the solution So from there, sometimes distance is also confusing. 1.33 sometimes carbon double bond distance. We can also take it as OH. So it depends upon how you have the expertise and what atomic scattering factor you are giving. If you are giving wrong atomic scattering factor, your result never converge, it gives you error. That's why here now C profile is very, very important. There should not be any level, any error of A level or B level now. Your structure is not accepted. So earlier what happens, say 10 years back, whatever sample you synthesize chemistry people, they send it for publications. So depending upon the reaction and NMR they accept. Now they say no. You verify your structure first with the X-ray crystallography. You supplement your results with crystal structure. Only then they accept it. So recently I have got one structure, in that case 85% structure came same, but 50% of the molecule is coming having NO2 group also. So two molecules are coming. Chemistry person says it can never happen, but he has put the solvent having cyanide in it, so that CN group has made some kind of reaction with the molecule and their nitrogen is coming. So crystal structure cannot tell lie. That is the point. So now their chemistry reaction is different. My crystal structure 15% is different. They are not ready to agree, but my data is publication quality. For a crystallographer or any referee, he will accept my structure, not the chemistry person's structure. That is my point. Is your doubt clear or not? I can further explain.
Yes, sir.
Because
It's clear.
whatever I do right,
I have.
program will take atomic scattering factor of that molecule only.
Yeah, now I understand. Yeah. So I have one more question.
Yeah.
Sir, as you have said that we are getting we are getting the intensity, whether it is constructive or destructive, it is coming from.
We have to find out everything.
It is coming from the setup place, right? So can we have a diffraction factor
coming from the because X-rays are falling on the sample, electrons are vibrating with the same.
Yeah. Sir, my question is that. Sir, my question is that can we have the information in the X-ray diffraction pattern of monolayer graphene?
No. The graphene as such we can find out the structure. Powder work I have not done. My expertise only on single crystal. I have never worked on powder.
No. For any 2D structure, if we can make a monolayer, can we have any information from the X-ray diffraction pattern?
Powder diffraction, you can make a thin film of that and then you can get some idea. You cannot go to the unit cell level, but you can get some idea what is your unit cell parameters, what are the interplanar spacing. Anyway, single layer, you cannot make a thin film of only one layer. It is how it is possible.
No, but in graphene it is possible. In graphene it is possible, and people are making.
You can do only the surface studies. I don't think you can go to the crystal level that molecules are sitting like this.
Okay, sir. Thank you so much.
The graphene, I don't know how to crystallize it.
I even also don't know, but just I am curious that if we have a monolayer like structure of any 2D materials, can we have any information from the X-ray crystallography? Because there are other techniques. I mean, people are using Raman and other techniques.
A lot of powder work has been done on these kind of materials by making thin films of these kind of materials.
Yeah, from powder it is possible because we have. From powder it is possible. Yeah.
Single crystal anyway, we have to mount it on the glass fiber. So
Yeah. Some substrate is needed for growing monolayer graphene or any 2D material. We need some substrate. It can be any substrate. So that's true. Okay, sir. Thank you so much.
Minimum 0.1 mm size. So it contains thousands of layers. So here I will. I'm making.
Okay, thank you, sir. Thank you.
Questions from others?